Hello everyone and welcome to another video on science, geekery, and awesomeness. I'm JJ Billings and I'm very excited to be doing another video today. I have a really good excuse for being gone so long. In fact, I started a PhD program at the University of Tennessee this semester. It's the second time around, which is totally cool, right? Like, second time's the charm or something? I'm not making that up. It's real. Go look it up. Needless to say, I've been pretty busy and I haven't had time to do a video. The first thing I wanted to do when the semester was over was do another YouTube video. And in fact, I did actually. It was just distributed through Oak Ridge National Laboratory's channel. So what I'm going to do for this video is basically just phone it in, say some stuff here, and then attach that video at the end. You might like it. It's on what I do for a living. It's on the Eclipse Integrated Computational Environment. It's pretty cool, I think, and I hope you enjoy it. So check it out. It is extremely technical, but I figured since this is supposed to be a show on science, I should deliver a little bit, right? So this is a very scientific video you're going to watch, and it shows a lot about my work. So enjoy, and I really hope you do. Of course, as usual, leave comments about it. Let me know. Tell me what you think. It's very long. Again, it's about like an hour or something like that. So that's that. It'll come on after the credits roll. And so what else is happening? I'm pretty busy. But between now and when I go back to school for the winter semester, I'm going to try to do another video, at least one more. And then when I get back into school, maybe I'll try to do one every month or so, just because that's about the most I'll have time to do. I've got a whole list of them, like things that I want to do, but just haven't been able to do. And look for some more. And the last thing is I hope that all of you have a very Merry Christmas. If I don't see you before then, have a Happy New Year. As always, be safe, drink responsibly, and of course, if you must drink good beer, and and have a good one. So enjoy. Thank you very much for watching, and as always, please subscribe or leave me some feedback on Twitter. Just not here, Twitter. All right. Thanks, everyone. Have a good one. Bye.
All right, so we'll go ahead and get started. Hello, everyone. For those of you who don't know me, my name is JJ Billings. I am a member of the research staff in the Computer Science Research Group. I guess I technically started here as a graduate student in 2006. It seems like it's been forever. But for the past few years, I've had the privilege of being an astrophysicist in a computer science group, and it leads to some very interesting things I'm going to tell you about today. I will beg your forgiveness and ask that you stick with me a bit on the technology. We're doing a lot of really interesting things here. This is streaming live to YouTube, which is pretty cool. But also my slides are actually done on Google Slides. So some of them may cut out, but there's a button I can click. And so we'll see how it goes. Andrew's talk, thank you, Andrew, was a good introduction to the Eclipse Foundation. And what I'm going to tell you about is Eclipse ICE, which is ORNL's modeling and simulation user environment. And of course, I'll explain what all of this is, if the mouse works. Okay. So, a brief outline. I'm going to talk to you a little bit about usability, and I think that's an important topic. And then I'm going to tell you about the problem and our solution, and then I'm going to spend a whole lot of time on applications. And for that, I think it's really worth it. even though it's between us and getting home for Friday night. So there are some QR codes here if you want to learn anything about the project. Also, we have an Eclipse page, being an Eclipse project. A lot of things are in transition right now because we went from a roughly 5-year-old project with SourceForge and all of that to a brand new Eclipse project. So there are links to half the servers on the internet. Okay, usability. What I like to do with this slide is say, just show of hands. Who knows what usability is? What? I've got one guy in front. Okay, two. All right, good. All right, so we got a few people. This is the best way I can think of to explain it. So we have some matches that are a centimeter long. We have a flower pot with the handle under the spigot. And my personal favorite, actually, is this phone. And when I first saw this phone, I was like, yeah, I would love to have a cell phone with a rotary dial on it. But then that's actually not all. If you look closer at this, the numbers are out of order. So what I learned on my grandma's phone as a kid will not work on this phone. This is impossible. So usability, in its simplest definition, is the ease with which we can use our technology to accomplish our goals. And I like to argue that usability goes to accessibility. That is to say, usability is what gets our advanced techniques and capabilities as a laboratory out the door. And so we have to think about, when we're making these codes, how can people get access to these capabilities when what we have traditionally developed, and I know this is a bit of a strong statement, is the computational equivalent to a bear trap. And if you look at this bear trap, I mean, it's got all the good stuff on the inside, right? I mean, there's some PBR and some smokes, and there's a camera that's older than me. But the thing about this is, we got all this good stuff, but getting it out of there safely requires a lot of training. And this is analogous to going to use some new, maybe physics capability in a big multi-physics code. I have to have a lot of training to go in and get that capability. Well, the second thing is the very framework that capability exists in might be rusty with some sharp edges. That's certainly a challenge. And then if I want to add a piece to that, that is not for the faint of heart. Because like the bear trap, if I press a little too hard in the center when I try to put my smartphone in there, it might just take my hand off. And so it's a bit hyperbolic and fun, but I like to compare the usability problem we have to this system. So I would argue that making it easier to use a code naturally exposes all the capabilities that we have. It masks the complex design, and that complex design is necessary. But it masks it. And it enables users to explore, to go out and to do things that maybe we never intended and maybe, they only dreamed of. Now, in modeling and simulation, usability is an interesting topic. In the rest of the world, this is my Twitter account. If I want to send a message across the world, or actually most of the time the way that Andrew and I talk, is by Twitter. I reach in my pocket, I pull this phone out, I start sliding my finger, and 10 seconds later, I've sent a message to Andrew in Canada. Now, that is arguably a complex system, and that's something that's hard to do. That's why we didn't come up with it until 2004 or something like that. But now, on the other hand, if I'm going to run my Fusion code, and apologies to Sophie, this is an older piece here, I have to put in all these commands, and I have to know what field splitting is, and I have to know how to set the final time in PETSI, and I have to know all of these things. Really? I mean, is that really what I have to do to run a code? Now, of course, in this particular example, we've since changed it. It's much easier, but there's still a lot of rules that I have to know. I can't just go in and find the box that says time step and change that so it ends at a different time. What's the problem, I ask? And we've spent, at the laboratory, we've spent a long time looking at this problem. And we know this problem. We've dealt with this. So, being a physicist, I like to reduce, reuse, recycle. And in particular, I thought that if there's a standard model of particle physics, maybe there's a standard model of scientific computing. So, all users have to do these things, and there are four activities that they have to do. Maybe there are more, maybe we could argue that there are less, but these are the four that we have identified with this project. Users have to define the problem, they have to run the simulation, they have to analyze the output, and they have to do something with their data. Here's where it gets tricky though. A lot of the formats that we use in the scientific world are akin to ancient Mayan, as shown in this picture. And I'm not actually just saying that to be cute, but they really are akin to ancient Mayan. They're block-based. The blocks can be out of order. The blocks can be merged with other blocks. Different fragments can be used in one block versus another. So we have this really complex input language in all of these different projects, and you have to know the rules just to get the input file. So I see Bronson in the back of the room may remember some of the galaxy work that I did for my master's, and some of they were cubic-shaped galaxies that came out because of the input file when we first started on that. And it is just because of issues with dealing with the inputs. So these are real challenges. Now, running on a simulator, here's another question I like to ask. Raise your hand, just, who's used a supercomputer today? Okay, yeah, So we have a few people who've actually used something today. How many people use Titan every week? Okay, we have a few people. How many people use a large cluster every week? Have a few more people. This is kind of the point here. These days, the jobs that we're launching are big jobs, and they're on big machines, and we don't always know the rules of running on those machines. And in fact, in the DOE complex, a lot of the new users we're picking up for our software, they've never used these machines. A lot of them in the applied technologies offices are people who have Windows machines, and the most they can hope to do is connect remotely to a server in the back of the room. Now, analyzing the output, I remember when I first started in scientific computing, every now and again, I might find an ASCII text file, right? And I could just go in, or I could run grep. I didn't even have to open the file, and I could get my answer out. Those days are gone. We're looking at large binary files these days, and if we're lucky, someone will write a post-processor that converts it down to something for us. And that's a very big challenge. I have a lot to show you about that. I will point out, though, for anyone who doesn't speak binary in the audience, that is binary written in binary. Lastly, archiving the output. This is a big challenge. I'll admit the red question mark means that my team has we've not really tackled this because it's a big issue. But in our communities, we have a lot of different requirements on the data that comes out of simulations, the data that goes into it, the executables, the source code for those executables. For example, in the nuclear community where we do a lot of work, if something is used for a license evaluation for a nuclear reactor, it has to be stored on hard disk, and maybe in some situations on tape, for 40 years or the life of the reactor, whichever is longer. There are some nasty challenges. And I would argue that everyone who is a super user of any given code thinks these are easy. And to be honest, we might even say, yeah, I could go use that other code and it'd be easy there too. I think, in my own experience, that works. Codes. Maybe if you've got a six-pack and a Saturday night, maybe you can get a few more codes. But it's challenging. If you are a novice user to any code package, you're going to have trouble with it. And new users who are not super users or experts are going to have trouble with it regardless. Okay, now, a lot of people come to me and they see that slide and they say that's too high level, it doesn't cover all the workflows. More or less does. Remember, this is not, what I've shown here is not a workflow, it's a set of activities. And so I'll point out that the arrows in this case, if you look at the bottom, that's really interesting. If you look at the bottom, there's a key there. So normally what we find, there's kind of a standard workflow that people go through with scientific codes. And they're going to set up their file, and they're going to run a job. They're going to analyze the output with visit or something like that, and then they're going to analyze the data. That is the task that we put our graduate students through, right? All day, every day, do those things for us. That's not the only case. Single use, a lot of times we say, excuse me, could you generate this input file for me? I will go run it. So-and-so will take a look at it, and then finally we'll get someone else to put it on hard disk or something like that, or a CD to ship it out. That's the single use case, where someone is only going to do one of these activities and ignore the others with the platform. The other one that we have, kind of multi-input, where someone comes in and they have n different input files that they have to generate. There's another one too where there's multi-output. I ran out of space for arrows. And then the last one we like to call the rerun. And that's where people come through and they have their input files, they run a job, they look at the results, they run another job, and they look at more results. And we see that one a lot. We get a lot of people who they don't really care about anything other than just running something and getting a look at it. So these are things that you mix and match to accomplish a goal. And there's quite a bit there. These are 4 of the things that we've looked at. In fact, there are actually 8 that we've examined pretty well. And some of them, I mention them a little bit later in the talk, but these are the most relevant ones. Okay, now so here's the little hiccup I said where I got to hit a button. Okay, so I suggest a cooler model of scientific computing. And why don't we have a computer do this? But right, like with Twitter, I don't have to ship a letter across the world and have people do it. I just send it from my phone. So why don't we build a smart intermediary? A smart system that can go in there and handle all of these rules and details, and they know where the brackets go, or they know where the less than signs go. They know how to do all that. Maybe they can do error checking. They can figure out what the file format is. We can just put all those details somewhere and codify them, and we do it for your code, and we do it for your code, and we do it for mine, and then when someone else comes along, they don't have to do it. And we interact as users with that smart intermediary, and it handles the job. I would assert that most of the stuff we do, most of the stuff we need to do, in fact, can be encapsulated for ease of use and automated almost entirely, and we can even make it better doing something like this. Case in point, since you guys kind of already know this is an Eclipse-based project, case in point, when you're writing code, I mean, a big IDE makes your life a whole lot easier. It takes a little work to get started and get it off the ground, but then you get a lot of benefit off of it. It's the same argument here. Okay, so let's go back to that thought for a second. This is possible. If this is something that we can do, why don't we do it? Let's just do it, right? As a community, this is something that we can tackle and get done. Okay, so we have, in my opinion, done that. This is something, I'm going to show you a lot of examples. This is something that we've been doing a really good job at. And that is the Eclipse Integrated Computational Environment, ICE. Some of you may know this as NICE, the NIMS Integrated Computational Environment. In fact, that's where we got our start. Years ago, David Bernholt and I came up with this idea, and we ran with it. And then it was just in the past 6 months or so that we've become ICE. Same project, same code, just an opportunity to get out to more of the community. Now, in some places, we're known as JADE. And we have a paper published where this system has been applied to quantum computers, particularly adiabatic quantum computers. So there's more. If you want to know about that, talk to Alex McCaskey over here. Throw your hand up. Talk to that guy. Okay. Doesn't do this with every slide. Okay, so project details. Some of this may be a little out of date, but it's more or less still the case. We are a 100% open source, cross-platform, general-purpose user environment. And you just go to the internet, you get us, we're there, and we can be applied to all sorts of problems. We are primarily developed at Oak Ridge National Laboratory. There's a lot of the dev team over here. We have a few former members of the dev team in the room. On average, we sit at about 7 or 8 members at a time. And We have some support staff that help us out on this, and our goal, again, is to make life easier for users and developers. Out of the 4 tasks that I showed you, we do 3 of them really well. I think we do them quite well. The data one we haven't touched. My sincere hope is that someone else will solve the data problem and give me an API that I can call. Okay, code details. We produce both binaries and source code. Again, we want to make life easy. I can tell you one of the things that drives me nuts is when I go to a conference, or worse, I get a phone call from maybe someone who pays me, and they say, you have to use this code, or I get the idea to use the code, and then I can't build it. That's terrible. So we produce binaries. And you can go to the website on here, and you can get a binary. We don't want to burden users with that. As far as the code base itself, I haven't counted in a while, and olo.net broke. It stopped counting around, I think the whole thing, including comments and tests and everything, we're sitting at around 315,000 lines, and then there was some problem. Our latest estimates is that the entire code base is at 500,000 lines of code. And there's a lot going on there. Exhaustive unit tests. So fully half of that number. We got 500,000, 500,000 lines of code, 250,000 lines of code are tests to make sure that this thing works right. That's what you have to do when you have nuclear in your name. So NEAMS, Integrated Computational Environment, the N in NEAMS is for nuclear, and we have to make sure this thing works. We have tons of documentation, and we have everything. Wikis, UML models, JavaDoc, Doxygen, you name it. We have a lot of sponsors. This is not a comprehensive list by any means, and we're hopeful that we'll actually do our first release through the Eclipse Foundation in FY15. Right now we're an Eclipse project in what Andrew called the incubation phase, where we're going through the review and doing all these different things. So hopefully that will be done soon, but we are available on the Eclipse servers. The estimated cost is a little old here. It's an old picture, I think, but it is spot on. And so our estimated cost this year is about $2.5 million over 5 years. An estimated 35 years of person effort. That's a very interesting number, and in fact true. Everyone who works on the team now and who has worked on the team in the past has put in a backbreaking amount of effort to make this happen. So the entire source base is 3-4 years old, and basically we have people that have just worked on it tirelessly so that we end up with about 3 years per person, per full-time person on the team. There's some C++. There's a real-time updating library that's in C++. Some of the other things I want to show you have C++ bindings so the simulation codes can get to them. And basically, how does this platform work? Now remember I told you that we have all these codes, and we have all these tasks that we want to do, and we want to plug them in. How does it work? So from a developer perspective, you write a plugin. Download Eclipse, generate some code, and in fact, some extensions can be done just by giving us a file. So we can do wonders with an XML file. And we're updating some stuff we have so we can do even more with it. And basically there are 4 parts of the framework or platform. I prefer platform. So there's the client, that's the UI piece. You never have to write any of that. The core, you never have to write any of that. The data structures are things that we work on, again. But the item is where you write your plugin. So finally, if you're a user, you just kind of go and download a binary for your platform. You unzip a file, that's it. Now that depends on data files. If there's some export controlled data that you need, or if there is maybe some proprietary stuff, it's kind of on you to go get that. We can't distribute it, and presumably some other people got that for you. Otherwise, you point and click. Back to how you do development with this. I'm going to cover about 5 or 6 slides on development. You'll see why when I get to the end. Everything in the platform is registered as a dynamic service. You guys know what that is? Room full of software developers, I think, yes? Okay. So, In short, if there's anyone that doesn't know, basically at runtime, the system starts up and it scans all the code it has and says, I have these services, and maybe I have 5 services and I have 50 implementations of those 5 services. So everything can be reused and plugged and played, and you can get what you want out of it. Everything in NICE is a reusable service. The item is the core class that does the work for building those input files, for launching those jobs, and doing different tasks like that. And a lot of it's already done, because we've done this for 15 different projects or something. You just subclass from item, and most of the work is done. Now, if you have a special format or something, you need to write some readers and writers, but when that's done, there is an I/O service where you get your stuff for that. The idea is that your business logic goes in your subclass of the item. My business logic goes in my subclass. And everything else in between, marshaling the data, drawing stuff on the screen, you name it, launching jobs on remote machines, that's the platform's problem. We shouldn't have to rewrite that code. Okay, other things that go in, some things we have, it's like, well, they don't really make sense in this construct of an item, so just add them as a tool to the platform. Visit, for example. We're starting to integrate ParaView as a tool, and that's just coming on an environment. We have some other tools as well. Okay, so if you were going to make one of these, this is how it works. In the top left, you see the item builder interface. That's the service interface. Realize that interface. Very easy. You can see it's a few operations. Basically, it says, what am I? Here's my type. And then it gives a little operation to construct this thing properly. This is a builder pattern. It's a very common software engineering pattern. And what that does is it will create an item with a concrete type. So in the bottom right, there's something called my first item. And that class only has a few operations it needs to realize. Depending on whether or not you have a standard format or something that we already support, or if you have a custom format, you could make this, and if you have an INI format, for example, we can be dumping an INI file in a very short amount of time. But if you have some custom format that's crazy and mixes things and requires the planets to be aligned to be written correctly, it might take us a week or two. Okay, so that's kind of how the pieces lay out. And then once you do that, once you write those pieces, you write another little file that says what your service is, all of a sudden when you restart the platform, it becomes available. It just shows up, and it's right there in the UI. Now, everything that we've already done is available to your plugin. This is the activity diagram. It's a flow chart. Basically, this is how it works. I will go through this, but I'm going to have to read it. So forgive me, I'm just going to be staring at this monitor, and you guys can check those ones out. So we start in the user column, and what they do is they say, I want to perform a particular task. And there's a little button they click, and they do that. The very core part of NICE, the platform, takes that name and dereferences it and say, that would be an instance of something created by this service. It does it. That service then sets up a form with everything they need to answer. So it's kind of like you go into the DMV, just not as slow. And you go in and it says, you say, I need to get a driver's license, or and they give you a form, and you fill it out, and when you're done with it, you ship it back. They review it, they check it. If they need more information, they flag you down, here, do this again, and then it comes back, and they say, okay, it's ready, what do you want me to do with it? And you say, well, I'd like you to go run a job on this machine, or just export the information to another file format. And it does it, and then it's done. So basically, it just zigzags back across the thing until it gets to the bottom. That's the workflow. Now, the user on the leftmost column is a person. On the rightmost column, the my first item, that is your code. Everything in the middle is our platform. Things to keep in mind again, you only write your business code. You don't write a bunch of platform code. You just write your business code. I'll give you some examples in a minute, but basically that's like if you need a parameter, if the user should specify a final time step, then that's a parameter that they need to fill out. We provide all the marshaling, unless you want to do something special, and there are hooks all over the platform for you to do that. And we really only want to codify what's needed. If someone has a preprocessor, we will use the preprocessor. And we do that with several codes where we just connect into an existing preprocessor. If that requires a system call, that's no problem. If it's Java code, we can integrate it in. It's no big deal. Okay, so then once all of that's done, maybe you've went in, you've written your business logic. Basically, you describe what the user needs to give you. You don't have to write any of the other stuff, again, unless you have custom I/O formats. Everything is backed by very sophisticated tools once you give us the data. So for example, as a visual representation of this, consider this table. It's a table. Who cares, right? Actually, that's a really complicated table. And to build that in a generic way, where anyone in this room can come in and use that table, is very challenging. That table, you can turn items on and off. The columns can be things that you enter in automatically, or they have drop downs and bounds and all sorts of stuff. They have comments which are written out if the thing is written out, or they're not, depending on what your parameters are. But the whole point of this is, once we standardize everything to a good IOR, a good intermediate object representation, we can just make things like this and they just work. Different views of the same data to illustrate that point further. So on the top, I did something that I generally hate to do, and I haven't done in a long time. I put code in a talk. But this is to actually illustrate a point, and it's not real code. I just made it just for this. So on the top left is some XML. On the top right is some Java. Those are logically equivalent to the same pieces at the bottom. And at runtime, based on what you tell us about that data, we change how it looks. For example, if you say, I just want a number, I just want the current flux, right? Something like that. That's a battery thing. Then that is in, if you look at the electrical properties box in the middle right, that's just a raw box where you put something in. But if you say, I have a list of things where you should select something from it, in this case on the middle left, that's a drop-down box. Again, this is with the battery example. But finally, if you say, well, these would just be better organized as a table, or my stuff takes a table, then we take that same entry at the top and we can show it in a table. It's the same thing under the hood. It's either the XML or the code. We have some other markup languages we can deal with. It's the same thing. But based on what we know about it, because what you wrote down, we can present it differently and in ways that are very intuitive. So, okay, that's enough. Before anyone really falls asleep on me, I'll start putting some pretty pictures up. And, yeah. It is, yeah. You're the first person in years of putting that on talks that has noticed. Thank you. So, how about a magic trick? And I just remember, a picture is worth 1,000 words, so this is going to be very picture heavy. Also remember, everything that you see in these next slides is 100% reusable, and everything that you see here is actually from the platform. It's actually in there, and if it's not, I'll tell you that I took the picture from somewhere else. Okay, including these pictures, except for that weird arrow. Second arrow got a little weird. Okay, so domain-specific views. What we deal with in some cases, this is a nuclear reactor case with sodium-cooled fast reactors. What we deal with in this case are some custom views where people want to come in and they say, I don't want to look at a mesh with my results. I hate meshes. Get them away from me. Sometimes we run into people like that. And so we made some domain-specific views. They're backed up by data structures that can be viewed in multiple ways. But they actually do something really unique, and we have built a system. It's domain-specific. It kind of gets you by raw data, which can be messy. And it lets you go through the reactor in a way that is completely hierarchical and matches the real structure of the reactor. I left out some examples of doing this with LWRs, but we've done it there too. And this is the first time that I know of that anyone has kind of gone through and created a good hierarchical model of LWRs and SFRs and plants on top of them, and they can all be exchanged and moved around and visualized. This system is actually back-ended by HDF5. And so someone can use our C++ library, and they can say, I have a reactor, I have some data, and then that, when they say they're done, it'll write it to a file, and then on the user side, we can automatically load that up. Pretty handy. User never knows about that stuff in the middle. So what we can do once we have that is we can enable visual comparative analysis. And we have a paper that is submitted right now where we show this, and we show it for a particularly interesting case. This is real data from a real simulation. And what we have on one is we have a reference case, and then we have another case that is just data from a simulation that we've run. And what's really cool about this is, well, we can actually see them, but it's basically point and click to graph it. It's no more, oh, let me open GNU plot and let me type in, set X this and plot, 1:2 and all that stuff. You don't do that. It's actually, you click a button and say, I want to see these, and it plots it. But then we can do really cool things, because remember, we've got all of this in a format that we know and is standard. So we can make it possible to go ahead and run operations, such as in this case, a % difference. Now the reason it looks random is because they're really small differences. But this is comparing the reference case to the input case. And what we do when we do this is we take, for someone who's trying to do this analysis, from hours or days, or in the worst case scenario, longer than that, to minutes. And that is really great. On top of that, everything can be exported from the platform. You click a button and you dump it out. Okay, so I gotta click a couple things here. So we like to integrate with existing tools. Okay, it died on me. Well, these are YouTube videos that were supposed to play along. We like to use existing tools. So we have support for Visit in the platform. We just started this week adding support for peer review. And in the top left corner is a video that shows it's the same output from a NEC 5000 simulation. And we've hooked it up so that we can look at one case is the pressure and the other one is the mesh. And I really wish the video was working, because it actually rotates and you can see everything live. So you have that file, and you can move it around and zoom in and zoom out, and it's all there. In the bottom right corner is another nuclear simulation, but this is a triso particle in a pebble bed reactor. And it's just 2D, so moving it around doesn't help much. But you just hit the button, and the time, it just kind of goes on its own. And on the top right corner, this is our 2D mesh editor. We've been working on this for quite a while, and we're starting to extend it to 3D, which is pretty cool. Basically, you can go in and for any given element, you can grab the nodes. You can manipulate the nodes or the edges. And in the bottom left corner, what we have is our 3D constructive solid geometry editor, where you can go in and construct things together. I'll admit the geometry editor doesn't get used a lot. It's a tool that we built and has never really been picked up, but the other pieces are in active use. And this one, yeah, I kind of flashed to it a couple times, but this one was actually, this is really cool. This is some SNS phonon scattering data, and we had 2 summer students, one on my team and another summer student at the SNS, Matt Wang on my team and Claire Saunders at the SNS, who looked at the platform and they said, well, we really want to extend the platform to have a plotting engine that just deals with CSV files and can make it really easy to do things with. They went in and did it in a very general way, And at the end of the summer, they handed me this picture, and they handed it to SNS mentors. And I think it's fair to say we were more than a little happy with them, right? They did a great job. And so this is pretty neat. We've tried it out on some other things. I forgot to put in another slide I had where this same system is used for data from a nuclear fuel simulation. But this is a reusable part of the platform. It's not locked to anything, so you can just go grab it and use it. This is a 3D model of a nuclear plant. It's pretty cool. And so I've been working on this one for a while. You can fly around this thing. Basically, it's pipes and heat exchangers, and there's a reactor core in there. We are really looking forward to having an opportunity to maybe take those pipes and heat exchangers and use them somewhere else on another type of project where they'd be applicable. And maybe, we can't really do much with a reactor core in a model of some other power plant, but any steam-based power plant we could apply the rest of the system to. And so where does it work? Well, we do quite a bit now. So on the right, there's a list of things that we're doing next year, or this year. And then on the left, there's some other things. On the left, I kind of had to pack some stuff in there together. That nuclear energy box would mostly take up this slide with the things that we've done there. Data analysis, we have several different data analysis systems in there, and we're looking to build more. We have papers published on some plans that we've done and some prototypes in the system for automatically doing things like clustering and classification with the system built into the nuclear reactor data. Batteries, our battery team is up in the corner up there. We've been working with the KBAT team for a couple years now, and we can kind of go end-to-end simulation with batteries. It's pretty cool. Quantum computing, we've done that for a while, and that's published in a computational science and discovery paper. We've done a lot with that. Basic 3D geometry and 2D mesh editing. I say basic because it is basic right now, but that just means there's room for improvement. The work that we have on our plate this year is daunting, especially because in addition to being a full-time staff member, I'm also now a full-time PhD student. So we have a huge amount of work this year, and we're going to get it all done. There's a lot of juggling. So we're doing work in fusion. We're doing work in advanced materials. We're doing work in astrophysics, particularly related to kind of kinetic theory stuff. We're looking at climate. We really haven't gotten too involved with the climate community, but we have some contacts there that are interested in picking this up. Buildings, we have done a little work with buildings with some of our local buildings guys here, and basically they had an XML schema. They saw our system and they were like, can these things talk? And the answer is yes, in part because of work that we had to do for advanced materials and batteries. So for advanced materials and batteries, we had XML schema files. And we built into the platform, we kind of turned some things on that's in the rest of Eclipse, and we built a little stuff on our side where we just consume XML schemas. We'll read that schema and say what is valid and what is invalid, and then we throw it on the screen and people can edit it. So when we got to the buildings work, we've started looking at that, and we've had some success pulling in stuff. There are more third-party tools that are going into the system. I mentioned ParaView. There are a few more. Andrew mentioned the DawnSci project, and I hope that we can merge a lot of our visualization and analysis stuff with the DawnSci team. We've had a lot of meetings to that effect. Supported projects. So I hope it's a full list. I really do. If I forgot anyone and you're in the audience, please give me. Batteries, KBAT and BAT-ML. Moose applications. If you haven't heard of Moose, it's a pretty slick object-oriented modeling and simulation framework. We support everything in the platform. Quantum computing, advanced materials, Cecina is one of the codes we're working with, and we're building a new reflectivity modeler into the platform. That's going to come in as one of the tools I mentioned. Instead of fitting into that kind of item socket, it's going to be a standalone tool. Viz and data, yeah, there's a bunch of stuff in here. CFD, NEC 5000. We've done some pretty cool stuff with NEC 5000. Or Viz and data, great. We have the mesh editor in there. And another nuclear energy one we've worked with is Proteus. There are a few more that aren't on this list because maybe we've done some stuff in the past and those projects have kind of ended. And then there are more that come up. This is a picture of a battery from KBAT. And what's really great about this is that we ran the simulation. We set up the input, we ran the simulation, and then this was a small case, took 5 minutes to run, and then we clicked a couple buttons, switched the perspective, and then loaded up these graphs. And this is, you can move that battery around, zoom in, zoom out, run time series things of it, and so it's pretty cool. The whole point I want to make with this is that we have one platform and we have integrated encodes into it. So this is like when you look at the Eclipse platform and you see all of the tools that are integrated into the Java IDE or the C++ software or whatever, you name it. Same philosophy here. We've brought all of these things into the one platform. So, I started 5 minutes early and I'm still getting close to running out of time. And so that's why I did not discuss all of these things. We are working on the web server version of ICE, and we're kind of officially working on that now. We've had something unofficial for a while. Basically, because the system is based on SWT and Eclipse RCP, there are some technologies out there that will take the same Java code and immediately translate that into a web server. So right now the way we work is they download ICE and they use it for themselves. They can also connect to someone else's version of ICE if they want to work with theirs. Maybe they have particular items in it. What we envision down the road is being on the web. You don't go to our place and download us. You go to someone else's place. So you go to ice.ornl.gov. Maybe you go to ice.eclipse.org or something like that, and you just run the system from there. We're adding project and repo support. So basically all the inputs you create can go to Git or SVN, or you can pull in other people's like that. Pair view integration, we're adding provenance tracking. That mesh editor is going to be a 3D mesh editor in the future. One of the things, we've published on this a little bit, but we haven't put it into production, is the automated declarative data mining, where basically you give us your data, we know the format, and you tell us some operations that you want run, and it just kicks off and does it. Auto generation of plugins from XML, that one is actually probably a couple days from done. Developer-focused productivity plugins. We've talked about adding all sorts of developer-focused stuff because we're using Eclipse, and it's all about developers. We have a lot of work on that, but what's really cool is that a lot of stuff already exists, and we can customize it both for Oak Ridge and for Oak Ridge's partners in some of these programs that we have. And cloud stuff. Everything in cloud should be classified as stuff because we don't know how it works. But we are doing some stuff with the cloud. And automatic updates. If someone does download the rich client, I don't want them to have to go download another version. We have the stuff in place to do automatic updates, and that is happening soon. And there are about 100 different other things happening. This was all I could come up with during a meeting this morning. Okay, so let me tell you why we joined the Eclipse Foundation. Andrew gave a good discussion on this, so I'll kind of gloss over these points and then go to what benefit we get out of it. I will say, though, that I guess there are over 270 projects now. I know there are over 250 because we were 251. And basically, it is a community for developing commercially friendly software. And it's kind of like the NFL of software development. So, Oak Ridge stepping out and saying, we're part of this organization. We work with the Eclipse Foundation and we're releasing code through there, is saying to the commercial world that we're very serious about being partners with them. It's saying to the applied technologies programs that we take technology transfer very seriously. So what do we get out of it, though? We probably wouldn't do it if that was the only reason. But there are some things that we get out of it that are really great. Andrew talked some about licenses, and this is a big thing for me. I have been burnt by licenses before. And what's really cool about the Eclipse Foundation is they check that for you. So when you submit, someone says, I want to give you a contribution, you put it in the system and they go through and check it. And lawyers check it, right? It's not just like I get it and say, yeah, okay, it's probably cool. No, actually people who do this for a living check it. And that's very valuable. The community is one that makes you stand up straight and very welcoming, definitely welcoming, but rigorous community that checks you at every opportunity. Common build infrastructure is pretty nice. We haven't started using it because we're trying to figure out how we can get everything out of those pieces, but it's great. We have been exposed to a large number of users at conferences and other places, and I have to admit, I think the day I submitted my paperwork was sometime in February, and more or less my phone hasn't stopped ringing since because of the high-profile effect that exists for the foundation. So a lot of people see this product at Eclipse now, and they're like, wow, this is really great. I want to use it. And, oh, here's the guy's phone number. I'll call him at home at night. So we have a newsletter coming out a couple months or so, and in January, and so it'll expose this to a very large number of people. 115,000? Yeah, so, publication is pretty cool, but when you know you're going to get distributed to 115,000 people, I think that. And again, this streamlines the contributions coming back to us. The process at the bottom is basically what it goes through. Someone comes to me and they say, Jay, I wrote this for you. Will you take it and use it? Oh, we need to check it out first. We need to make sure, Andrew's example is spot on. We need to make sure it doesn't have proprietary code in it. Because one of the great ways to really wreck someone else's project is to give them someone else's code. And get them sued. So it goes through the review, and they can give that code to us through GitHub or Bugzilla. They can give it to us through email, even. And then we put in a contribution questionnaire, it gets checked, and finally we integrate it into the project. So, a pretty straightforward process that helps out. Okay, so getting into the last phase of the talk, and I want to talk about our collaboration outlook. So if you guys thought that the talks and the refreshments were all for free, this is... So we collaborate with a lot of people. It's growing. It's really great. Last year there were, this time last year, only the two at the top on the slide. So it's pretty cool. So we have core developers, we have subject matter experts, we have contributors, Diamond Light Source, those are the Donsai people. And we've had a really great collaboration with them. And actually, the hopeful future contributors should change. We are working with Kitware now on the ParaView stuff. And I'm going to read this next part because I think it's really important, and I want you guys to actually hear me say it. Our goal is to foster an open, collaborative community that includes contributions of all forms from everyone and encourages constructive, positive discourse about and the implementation of highly usable open source modeling and simulation tools with a license, pardon my typo there, with a license that supports wide adoption of the platform. We hope to double the number of core developers and core developer institutions. So collaboration opportunities. We would like for you to get involved in this. This is a community project. Part of this going to the Eclipse Foundation, getting it off of my servers or my account at SourceForge, is so that everyone can own it. It drives me up the wall to produce a product for the DOE, and then it's like, well, yeah, he kind of really is the only person that deals with that. So now we have it out to the community, and everyone has this. So there are many ways that you can collaborate and contribute. Use the code. Test the code. Give us some code or give us something to code. We're fine with either of those. Provide feedback, develop documentation, tell your friends about us, and introduce us to some new technologies. We do have some funds available for interesting projects. If someone comes to me with an interesting idea that benefits more than one person, might have some funds available to support that. Getting started as a user, pretty easy. First thing you should always do is join the user mailing list, download it, check out our wiki for some tutorials, email the list if you have questions. If you want to get started with development, that's almost as easy. It's one extra step. Join the mailing list again, of course. We have a dev list. Download Eclipse, because if you're going to write code, you don't try to do this in NetBeans. So download Eclipse, set up your environment according to our build instructions, start playing with org.eclipse.ice.tableComponentTester. That is our test code. So every new data structure we develop, we put an example in this component, and as a user, you can go and mess with those pieces. As a developer, you can go and mess with the code for those pieces. Finally, email the list if you have questions. I think that's the last slide, actually. Yeah, so, thank you very much for coming. I'm glad you guys could make it. Of course, thanks to our sponsors. I hope some of the 4 YouTube viewers are you guys. Thanks for coming. And I'd like to thank my additional authors, both current, we have some current team members over here. We have a couple former team members, and I hope we have a bunch of future team members in the room. If you have any questions, I'd love to answer them. Any questions? Bronson. The mic.
Technical question and a less technical question. So, the visit examples that you showed?
Yeah.
Is visit executing locally and getting the data through a socket? Or
We can do
exactly are you doing that?
3 different modes, one of which is that one, locally through a socket. We can do a remote connection to visit on a server where we both launch it or connect to one that's already running.
The less technical question is, you had a bullet, but you skipped over it about future collaboration tools. Say anything more about that? It was under the developer tools.
Yeah, here?
Yeah, collaboration-focused extensions. I'm sorry.
Oh, I'm sorry. I skipped over it. Yeah, I don't know why, because that's the one I really wanted. Yeah, so a few years ago, I did a collaboratories proposal. Actually, Eric and I wrote one. And we had a bunch of really good ideas. It wasn't picked up at the time, but we're going to, this project is going to follow through with them. I'm not entirely willing to share them out to a big room, but basically they're looking at all these different things you can do to improve collaboration on modeling and simulation projects. You know, a lot of people think you put it in a repo, that's collaborating. But there's so much more to it than that. We want to be able to publish data files, both input files, and we want to be able to publish data that comes out of it, index all of that, and all sorts of stuff. But I'm happy to tell you more. Other questions? Good.
You said when people, you know.
Yeah.
What's the timescale? Is that?
Actually, if it's less than 1,000 lines of code, it's not reviewed. So we have received contributions already, and they were really short, and we didn't have to go through the review. If we get something big, if someone comes in and they develop a massive thing where they've spent weeks on it, and they're like, here, you should take this code, and it's like 10,000 lines of code. Even if it didn't have to go through the process, I would go through it personally and look and see what they were giving me. There was a really good example of that came out on the Eclipse dev list the other day about something that was auto-accepted where a person hadn't looked at it. And it turned out that that someone had basically exploited Garrett to get a commit in where there was a bunch of virus. There was a bunch of really nasty executable code that had been implanted as a script in an HTML file. And it was caught because a person looked at it. That answered, right? Okay. Any more questions? Yes, hi. We do actually. So we have some papers published where we were looking at different data mining techniques, and we have some follow-on work that we did, which we haven't published, that was actually looking at using Hadoop studies. So basically, in that nuclear reactor example that I had, there are some good classes that can be discovered through clustering. And so we did that, and we found out some pretty neat stuff that we just learned without knowledge of the data in advance. And as that data gets bigger and bigger, we're not going to do it with a homegrown code. We're going to have to use Hadoop or some of these more recent alternatives. Very good question. With qualifications that I say this without knowing exactly what you mean by the configuration, yes. You know, there are a lot of different things that we can change before we launch something. More questions? Okay, no more? All right. Well, I would like to thank you all again for coming to this, and I hope that you will grab some more refreshments on your way out. And let's thank Andrew for coming all the way down here.
And Jay for organizing one more time. Also, I've got some really cool free stickers if anybody wants them. I'll put them up in the front here.
Quick, some of my people get stickers first. No, I please let the people who don't have them have. I'd like to say thank you to everyone on YouTube who joined this. We're going to sign off. Thanks.
Hi, Mom.
Hey, Billings. I'm actually